All right. This is going to be predicting products with single replacement reactions, okay, using the activity series of metals and non-metals. So what you're going to need to do in your packet, now we're obviously going to use this in future years, this current year, it's page 94 and 95, or in future years, whatever page it's going to be, it's this page right here, activity series for single displacement reactions. So you're going to take a look at this. And I'm going to talk a little bit more in depth about what's being shown on that paper to give you an idea of how to attack problems like this, okay? And you're going to notice that I've said it all year, you know, don't just do the problem, think the problem, okay? And these are problems, equations, where you have to think them out. But the only way you can think it out is if you understood everything we did before, everything about periodic table trends, everything about what these atoms, when they form ions to get a full outer shell, why do they react? What type of compounds we have? Tell me about the atomic radius. Tell me about all of that comes into play here. Okay? So overall, we'll go talk through this page a little bit. Okay? And then I'll do a couple on the following page too. We'll talk them through. So this is just for single replacement. You will also get a sheet with decomposition reactions. There's certain rules for decomposition reactions. That'll be given to you also, okay? As far as double replacement, there are things called solubility rules. Unfortunately, we don't get that far here. So you will just assume that all of the double replacement reactions you'll predict all of them at this point. When you get to the high school, there will be some solubility rules that you'll follow to say, oh, this does or doesn't react. But you can pick that up down the road. This is pretty substantial for this point. Anyway, okay? So let's talk about the first one. So right now we've got aluminum plus PbCl2 yielding AlCl3 plus lead. Okay, now, so obviously it's a single replacement reaction. So how do we know? Let's just pretend we don't have this here. If we stick these two together, and we agitate, we add heat, we do all those things to speed up the reaction. Is aluminum, think of it this way, reactive or powerful enough to break apart lead, who is a transition metal bonded to two atoms of chlorine? So again, can we take aluminum, which is a somewhat reactive metal in group 13, 3 valence electrons, wants to lose 3 to get a full outer shell? Will it be active enough to displace, break this apart, push lead aside, and be active enough to bond with the chlorine, which will become a chloride atom? And obviously, without even looking at that chart, without even looking at it, yes, absolutely. Because transition metals aren't too reactive. Aluminum is more reactive than that. But take your activity series, which you will get on exams, take a look. So you're going to compare this metal right here to this metal. It's metal on metal. And you're looking, okay, where does this fall? So lead falls down here. Aluminum is above it, somewhat significantly. So yes, aluminum has enough energy to break apart this bond, right? And when we predict products, we pull the atoms apart. So you've got aluminum, you've got lead in this transitional stage, and you've got chlorine atoms. And we talked about before, way back when, what a physical and chemical change is. I know we talked about dissolving in water, bonds break through dissociation, but we don't have new bonds formed. They form new attractions and intermolecular forces, physical change. That you should know perfectly. Here, bonds are broken. Where do I go? Who do I go with? Well, this goes back to, do you know your nomenclature? Metal, metal, non-metal. Explain to me how you're going to have aluminum and lead react with each other. You tell me that. That's like what we call it, stupid sodium, Na2. Come on now, you know that's not right. So think, oh, here it looks like we can form an ionic compound, metal, non-metal. And aluminum has a positive 3 oxidation number, chlorine is a halogen, -1. They form AlCl3. You're at the point where you can do that in your head. And you know that over here we have lead, metal, by itself. Can it be by itself? Sure, it's not that reactive. It can exist alone. Okay, so you see how that makes sense? Again, look at how much we applied from what we've learned before to be able to do things like this. And that's the point of this course. Okay? Let's take a look at the second one they're showing you. Cl2 plus FeBr3 yields FeCl3 plus Br2. Okay, now, first off, what you should do on the top of all these predicting product things is write down Brinkelhoff. And you should not just know what Brinkelhoff is, you should conceptually understand why there's Brinkelhoff. Why are they diatomic? You know what we talked about? Well, can sodium be diatomic? Heck no. No, it can't, because they want to lose. All these guys want to gain, they want to share. Knowing is one thing, understanding is another. So when you predict products, I've seen so many times where kids will do this. Oh, this will be given to you like that. And then they'll do that, where bromine is by itself. So you're telling me a reaction comes to fruition and you're going to be left with a halogen atom all by itself. That's what you're telling me if you do that. No, you know a halogen is very active. It wants to react to get that full outer shell. And you need to understand that it's diatomic. And each of these, before it's balanced, it's 1 mole of each thing. So there's 10 to the 23rd of these. Of course, they're going to find each other and bond together. But see, that's all that conceptual understanding you already have if you've studied, worked hard, and apply what you've learned. That's the cool part of this class. Look what we're doing now. So anyway, let's go back to this. So let's say we have our reactants right here. You're going to take a transition metal, stable, bonded to 3 bromines. No problem. You're going to put diatomic chlorine in there. Now, here's the thing. What do we have 2 of? Up here we had what? 2 metals. So we had to compare their activity. Okay? We had to compare their activity. And we knew aluminum is more active than lead. We went through that a minute ago. Now, okay, what are your nonmetals? It's obviously iron is the metal, and your nonmetals are diatomic chlorine right here, and these bromine atoms right here. So these are the 2 you have to compare. So you take this chart, this activity series, and you take a look at where they are. Now here they go, they're all halogens. Okay, now here's my thing. Let's go back to way back when we talked about atomic radius. And we said all those elements in group 17 in the halogens. Fluorine, chlorine, bromine, iodine. Oh wow, they're ordered that way too in here. Now they're all very similar in their reactivity, we know. They all have 7 valence electrons, they all want to gain 1 valence electron. You know fluorine is in period 2, period 3, period 4, period 5, all 7 valence electrons, group 17. Okay? But if you had to say, which one of these would be the most reactive if you had to pick? Even though they're similar, you would know it would be, what? Think, they want to gain a valence electron. So this guy right here wants to gain, they all do, but this has the smallest radius, so that's why this is the most active. Okay, so now let's apply what we've learned before and put it here. So let's see, I've got active chlorine right here. It's more reactive than bromine due to the fact that it has a smaller radius. It can draw those electrons in due to a stronger force of attraction. You should know that. Is this going to be active enough to displace bromine over here? Given you know it's more reactive, and given you can just look it up on the table, but again, that's just doing the problem, which you need to do. Think the problem. Apply what you've learned. And you would know that, yes, this would be active enough to displace it. So then immediately you would think, okay, this comes in, rip apart. So you're left with iron atoms, you got bromine atoms, you got chlorine atoms. Okay, so now, pretend this isn't here. Let's think, not just do. Think. Now, who do I go with? Where do I go? We're at our peak craziness, peak energy. We don't know where to go. Who to go with? Because bonds broke. Now we got to form new bonds, and energy will be released. And we just learned that the energy level goes down because bonds are forming. It's an exothermic process. So overall, we ask ourselves, can we make this? Not really. What you make is this, an ionic compound, our salt, FeCl3, plus diatomic bromine. Because chlorine wants to come in, react with iron to get full outer shell. Bromine will be by itself. So again, the simple way is, going back to this one, aluminum is higher on the metal side of the activity series than lead, so therefore it's more active, it'll displace single replacement reaction. Here, chlorine is more active than bromine, it'll replace. Okay? So let's go to the next part. So we're going to go to the back part of this page. So it looks like this right here. Okay, hope you can see that. So let's take a look. It's interesting how much you can apply and understand. All right, so let's take a look at lead. Plus AlCl3. You know what that is, aluminum chloride. Okay. So now you got to ask yourself, single replacement, that's what we're setting up. What do we produce? Now look. You have lead right here. These guys are chemically bonded. They have a full outer shell. We know it's a metal, non-metal. We know it's an ionic compound. They transfer valence electrons. These all have full outer shells. So what do we have in common? Metal, metal, non-metal. So in the activity series, are we going to compare the activity of lead to aluminum or lead to chlorine? It's going to be lead to aluminum. So we take a look, and really, we know that lead is a transition metal. We know that aluminum is in group 13. It's pretty active because it wants to lose 3 valence electrons. So if this wants to react more than that, do you think this is strong enough to force this to break apart from chlorine? Absolutely not. This is no reaction. Okay, now, here's where you just do the problem. And we'll still show it. Look at the activity series. Lead, I know you can't see it, whatever, you can see it on your own paper. Lead is down here, aluminum's up here. Lead isn't active enough to displace aluminum, okay? So it stays like that, it doesn't react. And you're gonna have to know that. You will get this chart, but you're gonna have to, and you're not getting all this down here. You're only getting this top part, okay? You are not getting all this other stuff. You have to figure it out. All right, let's do the other one that they show you on here. Diatomic bromine. Okay, take a look again. Step 1, non-metal, non-metal, right? Remember how I told you to do that all the time? See how much it does help you understand? Again, it develops a thought process. I know it's annoying to write that on top. I get it. But there's so many different combinations and types of compounds and types of nomenclature and types of, reasoning as to why they are the way they are, that if you know in your head, if I'm ionic, metal, non-metal, I have this train of thought. If I'm non-metal, non-metal, I got this train of thought. It all builds. Here I got metal, non-metal. So now you should be thinking, I'm not even looking at this thing. I mean, come on. You got, what are you comparing? Non-metal to non-metal. We know bromine and chlorine are both very reactive non-metals because they're halogens and they're group 17, they want to gain a valence electron. Okay, that's back in October. Wow. So now let's take a look. Is this bromine going to be active enough to displace chlorine that's already stable and reactive? Now let's think. They're both halogens, they're both reactive. They both want to gain valence electrons. But bromine has a larger atomic radius than chlorine. So chlorine has a greater force of attraction to these electrons. So therefore bromine doesn't have enough power or activity to want to displace that. Therefore you've got no reaction. Okay? So that's pretty simple, okay? Overall. So that's your mindset. And again, you take the chart, bromine down here, chlorine up here, not enough to displace it. And I got a thing on the other reaction was the opposite way around, so you should see the difference, okay? So that's using the activity series for only single replacement reactions. And you're responsible for all those now. Okay, now, let's do 1 or 2. Go to number 1 and 2 where it says predicting products of chemical reactions worksheet. Okay. Now let's do a few of these, okay? So let's do magnesium bromide plus chlorine. So you have magnesium bromide plus chlorine. Now let's do this. This is where your nomenclature comes into play. Metal, non-metal, ionic compound, chlorine. Okay, well, hold on. Don't you dare do that crisscross. Okay? You know, and I'm not going to show you each one. You should do this in your head. It's MgBr2 plus Cl. You think that looks right? What should go off in your head? What should you write on the top of each paper? Brinkelhoff. Diatomic. Why? That atom would not exist by itself. It's always found chemically bonded to something else, and in many cases it's bonded to itself to form a diatomic molecule. It's a Brinkelhoff element because it's a halogen, it's very reactive. See how that works. Okay, now. Okay. Now the obvious answer is this. We're going to break this apart. Now hold on, but you have to ask yourself, go back to your activity series. Where is chlorine in regards to bromine? We kind of did this already. Okay? Chlorine is more reactive than bromine, therefore it has enough activity to break this apart. So then you're left with magnesium atoms, you're left with chlorine atoms, you're left with bromine atoms. Okay? So what are we going to have? Single replacement. You're going to need a metal-non-metal. Right? So what's the metal-non-metal combination going to be? Metal, non-metal, non-metal. It's going to be Mg, magnesium chloride, Cl2. You should know how to do that. Okay? Plus bromine, non-metal. Yay, we're done. Oh, wait a minute. Brinkelhoff, Brinkelhoff. Alarms should go off in your head. But that's just doing the problem. Oh, I memorized. Yeah, it's Br2 because it's Brinkelhoff, and that's why I know that. No. Why it's diatomic. Why it's a halogen. Two or more nonmetals. They both want to gain valence electrons. Therefore, they bond with each other to share, to form a covalent bond. Nonpolar. You need to understand that. Okay? Watch those diatomic elements. Okay? I don't want to see you, because you won't be able to balance it properly. I just want to make sure you get those down pretty well. All right. Good habits will help you down the road. Okay. You know what? Let's do something different. I think we've done enough of those. Go down to number 3 real quick on that page. And this is a double replacement reaction. Now, some of these will work and some won't. And at our level, they will. We're going to assume they all work. Okay? We don't have time to get into solubility rules, unfortunately, and that's okay. But as long as you can understand the mechanism of a double replacement reaction and think and predict what they would form, that's a good start. Okay? So we're going to take silver nitrate plus zinc chloride. Okay. Silver nitrate, AgNO3. EOA, EOA, da-da-da-da-da-da-da. Okay, good. You know that. Plus zinc chloride. Zinc is a positive 2 oxidation number, chloride -1. Okay. So now ask yourself, you got metal, non-metal? Metal, non-metal. Okay, now. You want to rip apart this. Watch this. Break, break. Bonds break. Remember what you learned. What do we need to get bonds to break? We need to add energy to the system. Bonds breaking, energy goes in, right? Breaks those bonds apart. We learned that through bond energy. Each one has a certain amount of potential energy stored in the chemical bonds. What do they produce? Okay, so right now we've got Ag. We've got nitrate floating around there. We got zinc, and we got chlorine atoms. So can we make, let's say, can we make silver zinc? Silink? No. You gonna put a metal and metal together like that? No. Can we make, what can we make? Metal non-metal, double replacement, ionic compounds, salts. So we had silver nitrate, so what can we make? Silver chloride. Oops, excuse me. EOA, EOA, plus 1, -1. Plus what's left over? Zinc nitrate. There you go. See how that works right there? Break apart, bonds break, energy enters the system. Right? Transition state, peak chaos. Who do I go with? Where do I go? Once new bonds form, we're getting full outer shells. Energy is being released out of the system, right? Because these substances are becoming stable. And as they leave the system or exit the system, product formation where bonds form is an exothermic process. And then you would calculate the delta H from before. I'm not gonna, that's another video. So I hope that helps you, okay? Here's another one. Keep this in mind. Go down to number 11. You'll love this one. easy. Hydrocarbon, 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 hydrocarbon. Kaboom! Combustion, easy, every time. Done. Okay? So that's a good start to get you started on these. Again, I want you to take a week and gradually work on these. Try them. Okay? You will actually like them because you're going to think, wow, I really know my stuff and I've learned a lot and look at what I'm able to do. Try your best with the decomposition. I'll probably spend more time in class talking about those decomposition rules. Okay? I don't have time to make a whole video on that because this is long enough as it is. But I think this will get you off to a good start, and then we can clean up things in class. But by doing this, we've saved a lot of time in class, right? So we can talk more in depth about the conceptual part of things. You know, we can now spend more time talking about solubility. We can talk more time about surfactants and soap and things like that. So we can really apply what we've learned. Okay, this is stuff you can figure out on your own with a little help of a video. Okay, so get it done. Get working on it. I hope this helps. All right, that's it. Later.